All right, so I said we'd review it for today. We haven't covered a lot of material actually since the past exam. I'll list the topics up here. So the material you're responsible for actually on the homework, it's homeworks 9 and 10. And so that would be, I think the best study plan. Again, I don't have old exams for you to review. And then we've covered really just chapters 7 and 8. Okay, we went into chapter 9 on interrupts on Monday, but there will be nothing on the exam related to interrupts for chapter 9. Okay, I didn't give you any homework on it. We just barely got into the material. Does anyone have any questions? Yeah.
There was a specific homework problem I had a question about.
Sure.
It was, I don't remember what it was exactly, but you had to, I can look. It was one of the external interfacing questions. You could use like equal transistor. It was,
Oh, was that for like the solenoid or something?
yeah.
Okay. So usually, I mean, the interfacing there is really nothing special compared to the other like LEDs or anything else that we've got in space. So, so typically a solenoid or relay, they're designed to operate at a particular voltage, and then they'll give you a voltage and current, so you don't have to add any resistance or anything like that to it. So they're rated, you know, let's say it's 5 volts at 100 milliamps is the rating on the, well, I'll make it a relay. So you have 2 terminals to connect to the coil, and then when you energize the coil, the switch would close in this case. So the interfacing typically involves then making sure the transistor saturates and picking RB so that, picking RB so that it saturates. And the typical rule of thumb that I use, so here with hooked up to a 5-volt supply, you can assume that it's going to be 100 milliamps, because in saturation, this is usually 1/10 of a volt. So the 5-volt supply is going to be 4.9 volts. It may be a little less than 100 milliamps, but not enough to make much difference. We're going to estimate, we're using an estimate for the beta value here anyway. So I would assume 100 milliamps at essentially 5 volts. Now, to make sure the thing is in saturation, you just need to make sure the base current's large enough so that you know, if the transistor beta is 100, which is kind of typical, kind of a low value, you know, the ratio of base current to collector current would be 100 in the linear or active mode. So we just need to make sure that the base current's greater than that. It's kind of a standard rule of thumb is if the base current is 1/10 or 1/20 of the collector current, it's going to be in saturation, because that's such a small ratio. That ratio is much larger than the ratio you'd have in the active mode. So you just design for, let's say, 10 milliamps base current. Let IB equal IC over 10 to ensure saturation. And then the rest of it then is when we have to make sure our microcontroller is capable of supplying 10 milliamps. You know, ours in the high drive can supply up to 20. So we have to put it in high drive mode. And then our output voltage, high output voltage is 3.3 volts. We've got a 0.6, 0.7 volt drop across the base emitter junction in saturation. I don't know what you guys assume, 0.7, 3.3 minus 0.7 over 10 milliamps. So is that 2.6, 2.6 K, 260 ohms. I did that right, 3.3 minus, so 2.6. Yeah, I think that's right. Now there's one other thing you need to configure in the interface, and that's the Snubber diode here. Because the issue is when the transistor switches off and you try to cut off this current, that coil will generate a very large back voltage across it to try and maintain that current, and can exceed the rated collector to emitter voltage here on the transistor. So essentially all that you need to do You just hook up a diode like that. It looks, kind of backwards, but normally the diode does not carry current, right? So normally it would be hooked up like that. So normally it doesn't carry current, the current's going through the coil. But then now when you try to switch this off, if this generates a voltage to try and maintain that current, that current would actually generate since the current's decreasing, to try to generate it would generate a voltage with this polarity, which would forward bias that diode. Essentially, you've got now a path for that 100 milliamp current would allow it to continue to until the current dies away. Is that kind of what you were asking for in there somewhere?
Yeah, I was just confused about the Snubber diode and then how the current through the.
Yeah. Usually, 1/10 or 1/20 are fine. Just state whatever assumption you use. So chapter 7, just I'll put a brief list of topics. So feel free to ask questions if it prompts anything. So we talked about local and global variables, and then also lifetime, whether they had a temporary lifetime or a permanent lifetime, perhaps more properly, whether they have a function lifetime or an application lifetime. And so, I might give you like a little snippet of code and ask, is this a local variable or a global variable? Does it have a function lifetime, or does it exist over? So the other thing that comes into play there is the static keyword. And then also here, we talked about the stack primarily with regard to the standard passing convention between that C uses. If you're working in an assembly language, you don't have to follow that convention. But if you're writing an assembly routine, subroutine that you're going to call from C, or if you're working in assembly and want to call a C function, you'll have to understand the calling convention that the C compiler uses. And that's actually transferring the first 4 parameters in registers R0 through R3, pushing additional parameters on the stack, and then the return value is in register R0. We talk about fixed point numbers, and I think there was at least one homework problem on converting a formula to fixed point representation to avoid the use of the floating point processor. And this actually works really well in a lot of applications, and it's fast. Integer arithmetic is much faster than floating point arithmetic. We also looked at string to number conversion and number to string conversion. And there's some routines in the book there, but I don't think I typically just use scanf or sprintf to actually do those. I think, and especially there are special versions of those that are small. And then we looked at floating point numbers. Mainly, the point there was that these are different than the integer representations that we've used almost all semester. That they have this exponent and mantissa representation, binary decimal representation, They've got some details in the book. I'm not going to get too detailed on that. I may ask you, what power does a particular exponent, particular exponent value, what corresponding power of 2 does that represent? It uses a biased representation where you, for the exponent or something like that. I'm not going to get too detailed, and if there are any questions on that. And then chapter 8 is on interfacing. And we looked at the UART and SPI and LCD, but I didn't get into the details on that. We're actually using the provided code. So, and we've been using the UART code since early in the semester. So, for us, it's output init, and then after that, actually, you use the UART. I guess we could look at changing the baud rate, how to do that. The same for SPI. It was like SPI. The LCD, same there, using the provided routines. And then I will give you those, or if I ask you how to write anything to the LCD or something, you've got a project where you're doing that now. I won't have you form a bitmap image or anything like that by hand. So you can actually form these bitmap images just in using a drawing program or something like that. And then we looked at some of the problems like this. We looked at a scanned keyboard, how to interface with that, and then relays, solenoids, and DC motors. You get a chance to actually do any interface to a DC motor, but it's kind of where you'll pick up, I think, next semester in 454. So any questions on any of these topics or any of the homework?
Can you give an example with the 6-point numbers?
Yeah, I think there were a couple problems like in the book or something. That was chapter. So yeah, there's actually 2 kind of steps to that. Well, let me just make something up pretty easy. Let's say so that's an equation that you want to do, but just using integer arithmetic. So the first thing you do is we let our yi's be some delta times our floating point. Maybe a 1,000 or something like that would be appropriate. So you multiply both sides by this delta that you choose. So, and let's let delta equal 1,000. It would typically be a power of 10 or power of 2. So if it's power of 2, it's really nice because you can do the multiplications just by shifting, which is often even faster if you're looking for really high speed. Maybe 1,000, maybe a 10,000, something like that. We got, if you're working with 32-bit integers. So now this equation becomes yi as an integer, 3.65, xi as my integer, plus 1, 2, 3. So now yi and xi are integers, and they're both 1,000 times what the corresponding floating point number is. The last thing is actually to do something with this. And you could convert it to, so it's just using integer arithmetic with something like that, or plus 1, 2, 3. It might be an advantage to doing it like that. So this would be the corresponding fixed point integer representation of the top equation. Now, with the understanding that the xi and yi that feed in here are actually 1,000 times what their floating point values are. But you can, you use this formula just doing integer arithmetic. Let's say you get a yi of 9,000. That actually represents a y value of 9. So, but and you don't have to do, you wouldn't have to use the floating point processor at all. That would all be done in integer arithmetic. So there's actually two parts there. One is this scale factor, and then the other is converting any floating point numbers over to approximate decimal. Here we're kind of able to do it, exactly, except we'll get some rounding error here. So this is only going to be accurate to the 1,000th 3 digits. Anything else on that? I'd probably give you the delta value just to make it easier for me to grade. Because if I let everyone pick their own delta, then it's harder for me to grade. Or I could give you the integer representation and the delta and say what's the corresponding floating point or something like that. Any other questions? So we'll have this exam on Friday. We won't meet next week on Monday and Wednesday. The last project is due on Tuesday, so not on Wednesday, it's due on Tuesday at 11. Try to get it in before then. So it won't be accepted. I won't accept it late. Okay, so you got plenty of time to get it in early. You've got 0 time to get it in late. But I will accept it early, but not late. Any other questions? All right. So bring your book. The tests will be open book on Friday. If you're done with the project and don't think you'll need the book as reference for the project, turn in your book on Friday. If you still need it to work on the project, I'm not sure that you do, but you might. You can keep it and then turn it in when you check off the project. So the microcontrollers and the parts kits you keep, but the book you don't.